Welcome to Spring LIB.
So first, let's set up the problem and then we can talk about how to solve them. So let's say this is the grindstone and the direction of rotation for the grindstone is counterclockwise. That's why omega is in this direction and omega is the angular speed of the grindstone. So it's counterclockwise and there's a frictional force that's acting opposite to the direction of the angular speed, which is Fk, and we know that Fk is mu k times n, where n is the normal force. Now let's uh, change the omega naught value. So omega naught is the initial angular speed of the grindstone. So we convert from rev per minute to radians per second, and that's the conversion. So 850 revs per minute gives us 89 radians per second. Also, when the grindstone stops, it takes about 7.5 seconds to stop. So I think it's the better way to say that is t instead of s. So the total time it takes from omega naught speed to zero is 7.5 seconds, and the reason we say zero is because the grindstone stops. So omega final, let's write here, omega final is zero, right? um, Now we can use this following equation: omega final equals omega 0 plus alpha t, to find out the acceleration or angular acceleration that's involved in the system. So let's not worry about this first. Let's first calculate alpha, and then we can talk about the why the direction is in opposite, uh, why the direction is opposite. So from here we see that alpha is omega final minus omega initial, which is omega 0, over t, where this guy is 0, so we have 0 minus 89 radians per second, and we divide that by 7.5, which gives us negative 11.9 radians per second squared. So as we see here that there's a negative sign involved here, that means whatever the direction of omega is, the direction of alpha or the angular acceleration will be the opposite. So that's why we put a negative opposite sign or opposite direction of alpha here. So basically there is an opposite acceleration is acting, and that is due to this frictional force that's acting here. So the reason we're doing this is because we can figure out the torque equation, tau equals I times alpha, and using um, this equation with the frictional force equation mu k times n, we can figure out mu k. Let's see how we can do that. So if we apply this in this figure, we'll see that torque is equal to negative Fk times R, and the reason for that is because the normal force has zero momentum for rotation about an axis at the center of the grindstone, and therefore the torque is zero there. So the only torque on the grindstone is that due to the frictional force Fk. So that's why we only have negative Fk for our case, and again the negative sign is because it's in the opposite direction to omega. So that gives us negative mu k times nr. So we know that torque is equal to the translational force times the radial vector r. So in our case, the translational force here is the frictional force, and we multiply that with r. Right. Now, if we now apply this part of the equation to this, we'll see that I is basically half of mr squared, and the reason for that is because we're considering grindstone as a solid disk and the axis is through the center. So that's that. That means what we can do here is we can equate um, I alpha with this quantity right here. So that will give us half of mr squared alpha, which is equal to negative mu k in r, right? Um, Now from there we can actually solve for mu k. So mu k will be equal to negative mr alpha divided by twice n, where let's see, we are given n has 160 newtons, mass as 50 kg, the radial vector as 0.26 meter, and also alpha is something that we calculated, which was 11.9 radians per second squared. So if we use all the values over here, we see that mu k is 0.483. So we got rid of this negative sign here because we see that alpha is negative here, so there are two negative signs which makes mu k positive, and we see that that is 0.483, uh, and there's no unit there because it's just a coefficient. Thank you.